Good morning everyone. I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the next session of Dr. Kundan Tayade. Dr. Kundan Tayade is a sound academician and researcher having 11 plus years of experience in teaching UG and PG as well as research. Currently, he is working as an assistant professor in analytical chemistry at Rajshri Sahu Mahavidyalaya Autonomous, Latur. He is working on a minor research project sanctioned by Rajiv Gandhi Science and Technology Commission, Mumbai. He has published 28 research papers in A grade journals indexed in Scopus, Web of Science, and in renowned peer reviewed journals. He is extending research consultancy in sophisticated analytical instrumentation and corporate training. His trust area of research are supramolecular chemistry, molecular sensing, extraction chromatography, electrochemistry, etc. Two students are pursuing PhD under his supervision. Dr. Tayade has delivered many guest lectures and talks as a resource person in analytical chemistry and research methodology in various educational summits organized by renowned institutions. He has attended and organized many national and international educational events.
Hello, I am Dr. Kundan Tayade. I welcome all the aspirants on the board to online refresher course in chemistry organized by UGC HRDC Gujarat University Ahmedabad. So before going for the technical session, I would like to talk a couple of words regarding Gujarat University and the UGC HRDC Center. So Gujarat University is one of the pioneer educational institutes in India. This university is established in 1949 under the Gujarat University Act. It is having a well-established training center, that is UGC HRDC Center, and this UGC HRDC Center is always believing in experimentation and they are implementing their innovative ideas. As a result, they have bagged 15th rank in India. Also, this UGC HRDC Center in Gujarat University has availed a grant of 3.33 crores from MHRD under the RUSA project. So many adorable work they are doing. I wish all my regards to them for their further endeavor. Furthermore, I would like to extend my thanks, special thanks to Honorable Professor Jagdish S. Joshi sir, who is the director of UGC HRDC Gujarat, then Dr. Dilip Wasawa sir, the dynamic person, who is the course coordinator in chemistry. So my special thanks to all the dignitaries over here, that is the Joshi sir and Wasawa sir. It is a pleasure and honor to have such an opportunity to deliver the lecture in front of the young aspirants. So my topic is exploration on sophisticated analytical instruments. If you are having some recommendations or constructive suggestions, you can email me. Objectives for today's topic are to explore basic concepts in spectroscopy, to explain the instrumentation of UV visible, IR and NMR spectroscopy, and to highlight the relevance of these spectroscopies with the research. Now we will see what is the electromagnetic spectrum. So electromagnetic spectrum consists of various regions. It consists of cosmic ray region, gamma ray region, X-ray region, UV region, visible region, infrared region. The regions are highlighted here. So many regions are there. From cosmic rays to radio frequency wave region, the wavelength is increasing and the energy is decreasing. Amongst this electromagnetic spectrum, sorry, the ultraviolet visible and infrared region is constituting the light. Other radiation, other region is not called as light. You can see that EMR constitutes light as well as other radiation than light. We can say that UV, visible and IR is light. So what happens on the interaction of EMR with the matter, that we will see. We will consider here that the sun is the source of electromagnetic radiation. It is producing electromagnetic radiation, and this electromagnetic radiation is reacting with the sample. This girl is representing here the sample, and you can see that some changes are occurring in the sample when it is exposed to electromagnetic radiation. Similar is the case with the chemical substances or analytes. We are going to analyze that electromagnetic radiation is interacting with the sample molecules, and it is bringing changes in that sample molecules. Now, what is the concept underlying spectroscopy, spectrophotometry, and spectrometry? So you can answer in chat box. You are having the time of 30 seconds with you. What is spectroscopy, what is spectrophotometry, and what is spectrometry? Your time starts now. So I have already said that UV, IR, and visible region only constitutes light. So you can relate it with that photo word. Think about it and put the answer in the chat box. Yes, my friends. So we will see the interaction of radiation with matter, to whom we have to call spectroscopy, spectrophotometry, and spectrometry. So whenever there is interaction of electromagnetic radiation with the matter is there, it is called as spectroscopy. Any region radiation of EMR is reacting with the matter, then it is called as spectroscopy. But particularly, as I have mentioned, when the UV, visible, or IR region radiation is reacting with the sample, then you can say that it is spectrophotometry. So spectrophotometry, because photo means light, and this UV, visible, and IR constitutes light. We cannot say that NMR is spectrophotometry, because NMR uses radio frequency waves. Though NMR is a part of EMR, it is using radio frequency waves, which is not light. So you can say that NMR is spectroscopy, but you cannot say that NMR is spectrophotometry. Now, if some other radiation than EMR is reacting with the matter, then it is called as spectrometry. We have taken here the example of mass spectrometry. You can see that in mass spectrometry, we are bombarding the sample with high energy electrons of 70 electron volt energy. So it is not a part of electromagnetic radiation. So you can say that this is the mass spectrometry and not the mass spectroscopy. Now, the basic laws are governing this spectroscopy, that is the Beer's law and Lambert's law. It is collectively called as Beer-Lambert's law. Absorbance is directly proportional to concentration and path length. Here epsilon is the proportionality constant. If your concentration is in moles per liter, then it is called as molar absorptivity or molar extinction coefficient. If your concentration is in grams per liter, you can simply say that it is the absorptivity. Okay, so we are plotting here a graph of absorbance versus concentration of analyte. Then we are getting a straight line. Now, if you are deriving the slope of this straight line, slope or gradient of the straight line, that represents epsilon. So we have to always measure the absorbance at a particular wavelength, at the desired wavelength, that is the lambda max. What is meant by lambda max? So lambda max is the wavelength of maximum absorption, the wavelength at which absorption is maximum. It is not the maximum wavelength, it is the wavelength at which the absorption is maximum. That wavelength we have to focus. In case of KMnO4, you can see that 525 nanometer is the lambda max. We are also getting a side by peak at 529 nanometer, but the lambda max is 525 nanometer. 529 nanometer also we are getting a small peak, adjacent peak. Here you can see that the linear relationship between absorbance and analyte concentration makes this UV visible spectroscopy more suitable for the quantitative measurement. Okay, here one more thing we have to look for, that UV visible spectroscopy is a spectroscopy which is electronic spectroscopy. So we have to maintain the absorbance while taking the reading between 0.4 to 0.9. The absorbance should not be too low or the absorbance should not be too high. Why it is so? That we will see. If the absorbance is less than 0.4, means the radiant power of the transmitted light is as large as the radiant power of the incident radiation on the sample. So these two values are very closely related. They are too close and it will be difficult to differentiate between the radiant power of the transmitted light and radiant power of the incident radiation. So my friends, again our absorbance should not be greater than 0.9. If it is so, then we can see that the radiant power transmitted is very small and the stray light, which is unfortunately coming from some outside region of the instrument, that is stray light, it is called as unwanted light. This unwanted light is very small in quantity, but it is reaching up to the detector, and if it is reaching up to the detector, it will compete with the radiant power of the transmitted radiation. So your absorbance should not be very high, it should not be greater than 0.9, otherwise the stray light will compete with the radiant power transmitted. Now, how we can maintain the absorbance in the range 0.4 to 0.9? If the absorbance is too low, you can use a longer path length cell, longer path length cuvette. Okay, so absorbance is directly proportional to the path length according to the Lambert's law, so it will increase the absorbance. Further, what you can do, by some sample pre-treatment methods like solvent extraction, you can convert the solution of you can convert the dilute solution into concentrated solution. You can do the pre-concentration and then you can measure the absorbance. Okay, so if you are increasing the concentration, absorbance is increasing because Beer's law is there, absorbance is directly proportional to concentration. What happens if the absorbance is too high? Then what we have to do? We have to dilute the solution, dilute the concentrated solution to decrease the absorbance. Another thing you can do, you can use the cuvette of smaller path length. Even 1 mm path length cuvette is available. So you can use a lower path length cuvette, or you can do multiple dilutions also to decrease the concentration so that it will be in the requisite absorbance range. Absorbance can be converted into transmittance and vice versa. The scale is given. Absorbance is equal to log 1 upon T. This is the simple relationship between absorbance and transmittance. The few of the relations are given here. So absorbance is equal to 2 minus log to the base 10 of percent transmittance. Here 2 come from percent. For percent we have to multiply by 100. So log of 100 is 2. That's why absorbance is equal to 2 minus log to the base 10 of percent transmittance. So you may say that, so why we don't have to maintain the absorbance below 2? No. Our Beer-Lambert's law should be valid, it should be verified. That's why we have to keep the absorbance as low as possible, below 1, better below 0.9 and above 0.4. Okay, absorbance is not having any unit. Okay, now UV visible spectrophotometry we will see. I have already mentioned that it is electronic spectroscopy. The various regions in this UV visible spectroscopy are mentioned here. Vacuum region, it is called so because the vacuum we have to maintain, then only we can use the radiation of this region. It is not possible to use it in air because air molecules absorb this radiation. Now electronic energy level is there in the molecule. 3 energy levels are there: electronic, vibrational and rotational, which we are considering. In between electronic energy level, vibrational and rotational energy levels are placed. So UV radiation can bring out changes in all the 3 energy levels. That's why transition of electrons in vibrational, rotational energy levels will overlap with the electronic energy level, and we are getting a broad peak in UV visible spectrophotometry. Now we will see the instrumentation. The source is there, the source of radiation, we are saying UV visible, so two regions are there. The tungsten lamp is producing the near UV visible and near IR region radiation. Deuterium lamp or the hydrogen lamp can produce the UV region radiation, that is ranging between 160 to 380 nanometer. So source is used. You can bring it in position. One source will be in position at a time. Then next one is the wavelength selector. That wavelength selector may be the filter, it may be the prism, it may be the grating monochromator. Okay, so if you are using the grating, then 8,000 to 12,000 grooves are there per centimeter on the grating. So we can use filter, we can use prism monochromator, we can use the grating monochromator. Prism monochromator should be made up of quartz. We cannot use glass prism because glass absorbs the UV region radiation. So you have to take precaution that your wavelength selector, which is going to select your desired wavelength, is made up of quartz. Okay, so next one is the sample. So you can say that see that matched pair of cuvettes, which is called as sample cells, are used here. Their dimensions and their properties are same, their transmittance is same, their path length is same, the material of composition of the cuvette is same. In the reference cell we have to fill the matrix, we have to fill the solvent, and in the sample cuvette solvent plus sample is there. So sample cell is there. Again here the cuvette is made up of quartz. It is not made up of glass because glass will absorb the radiation, and if glass will absorb the radiation, definitely it will not reach up to the sample. Maximum radiant power should reach up to the sample. That's why the cuvettes are made up of quartz here. Then detector is there, various detectors we can use, that is photomultiplier tube, photo tube, etc. You can see that we can use the cuvettes for cuvettes of various shape in spectrophotometry. You can see that the most standard one or frequently used one is 1 centimeter fixed path length cell, then cylindrical cell is there, 5 mm path length cell is there, 1 mm path length cell is there, a longer path length cell, that is 20 mm path length cell is there. According to the need of the experiment, you can use different cuvettes. Okay, so these are the desired properties of the various component of UV visible spectrophotometer. My friends, you can see that there are 4 components: light source, then wavelength selector, sample cell holder, and then detector. So maximum radiant power should reach up to the sample. That's why the light source should be stable and it should produce the desired wavelength. Okay, then if the maximum radiant power is reaching up to the sample, then we are getting the good precision. If you are using the intense source, then radiant power increases and it is easy to see even the small absorbances. Then wavelength selector is there, which may be the monochromator. I have told you, you can use the prism monochromator or the filter monochromator, and you can also use filter. So a narrow band pass is used, which is selecting the desired wavelength. A very small band of wavelength is selected, or a single wavelength can be selected with the wavelength selector. Maximum radiant power should reach up to the sample. That's why we are looking for the large light throughput. Sample cell holder is there. This sample cell holder is made up of quartz. Its geometry is fixed, path length is fixed, it transmits wavelength of interest. Detector should be stable. It is converting the detected signal into electrical signal. It is detecting the signal and converting it into the electrical signal. It is sensitive to the wavelength of interest. Then we have to use UV visible spectroscopy for research. In case of the metal complex study, you can use UV visible spectroscopy. Here we cannot record the NMR spectra of the complexes of transition metals. Why it is so? That we will see in the next half of the session. You can see that in the metal complexes, metal to ligand charge transfer is there, then ligand to metal charge transfer is there, DD transition is there. All these phenomena can be studied by UV visible spectrophotometry. Then molecular recognition study. In fluorometry, we require the excitation wavelength. Fluorometry is one of the interesting branch of spectroscopy. It is emission spectroscopy and it is more sensitive than UV visible spectrophotometry. So, for determining the excitation wavelength, we have to use UV visible spectroscopy. From that, we can determine the excitation wavelength. It can also be used for molecular recognition study, which is one of the branch of the supramolecular chemistry, which is at the frontiers in chemistry. You can perform the whole molecular recognition study also by using the absorption spectroscopy, that is UV visible spectroscopy. Then you can study the highly conjugated compounds. Many more applications are there. You can see many dimensions where UV visible spectrophotometry is used. Okay, so I have given a link here so that you can explore many more examples where UV visible spectrophotometry is used. Now we will see IR spectrophotometry. So this IR spectrophotometry is the another region in EMR spectrum. So it is having energy less than UV visible spectrophotometry. So this IR spectrophotometry is divided into various regions. You can see here near IR region, which is also called as overtone region, then mid IR region, which is the vibrational region, then far IR region, which is the rotational region. Its wavelength in micron is given and its conversion into the wave number is given here. How to convert it? One simple example I have taken. Wave number in centimeter inverse is equal to 10 raised to 4 divided by the wavelength in micron. So if you are converting 2.5 micron into wave number, so 1 upon 2.5 into 10 raised to 4 you have to do. So you will get 4000 centimeter inverse. So this IR spectroscopy is IR region radiation is further divided into many regions. Functional group region, which is ranging between 4000 to 1450 centimeter inverse. Fingerprint region, which is ranging between 1450 to 450 centimeter inverse, and many more regions I have given here. Please explore that. Now we will see the principle of IR spectrophotometry. So in this technique, the chemical substance show absorption in the IR region. Not all the molecules are IR active. If the molecule is having the dipole moment, then only it is IR active. You can simply take the example of HCl. On HCl, there are charges, there are poles. The hydrogen is having the partial positive charge and the chlorine is having the partial negative charge. So you can see that the poles are created, and when the molecule is polar, it can absorb the IR region radiation. If the molecule is not having the dipole moment, it will not absorb IR region radiation. You can simply take a diatomic molecule, hydrogen molecule, H2. So H bond H is there, symmetry is there, no dipole moment is there, so it is IR inactive. So for being IR active, the molecule should have dipole moment, then the molecule is absorbing the vibration, it is absorbing the radiation in the IR region radiation, and it is giving the IR absorption spectrum. Whenever the frequency of the IR region radiation and the frequency of vibration of the molecule is matching, then and then only the absorption is taking place. Various bands are present in the IR spectrum which corresponds to the various functional group. My friends, we know that IR spectrophotometry is used for functional group identification. That is the primary goal of IR spectrophotometry. So functional group identification is there. Thus IR spectrum of chemical substance is the fingerprint for its identification. Which functional groups are present in the sample molecule, that we can come to know. then band absorption is identified by nu is equal to C upon lambda. We know that nu bar is the wave number and lambda is the wavelength, so nu bar is equal to 1 upon lambda. Okay, IR spectrum of ethanol, you can see that the various bands in IR spectrum are highlighted here. The OH stretching frequency is highlighted, then CS stretching frequency is highlighted. We know that the stretching and bending vibrations are occurring in the molecule. I will not go to that part, but here you can see that the stretching vibrations are highlighted here. It is having OH, the ethanol is having OH, so the band is there, a broad band for OH is there, then CS stretching band is there, it is in the range depicted there, and you can see that here the CO stretching frequency is given. This is the fingerprint region, which is ranging from 400 to 1500 centimeter inverse. A little bit difference is there in the literature reported, but near about the values are same. So now if you have a glance at this IR spectrum, you can see that on the x-axis wave number is there in centimeter inverse, and on the y-axis percent transmittance is there. While in the earlier case we have taken absorbance versus concentration of analyte as a spectrum. So why we are taking percent transmittance here instead of absorbance? That is the question. And again you can reply in the chat box. You are having 30 seconds with you. I hope you will reply. I request your active participation. In the earlier case, in UV visible spectrophotometry, we have recorded absorbance, but in case of the IR spectrophotometry, we are recording the percent transmittance. Percent transmittance means that transmittance is multiplied by 100. That we have to keep in mind. So why it is so? Okay, so we will see why percent transmittance we are recording. You can see, my friends, the value of absorption is usually very low and relatively it is less than 1. So while the value of transmittance is very usually high, it is easy to identify the weak transition more easily by looking at the transmission rather than the absorption. If spectral intensities are normalized, then that weak absorption peaks will be washed out. What is normalization? You can do the rescaling of data by considering the initial value, or you can do the rescaling of data by minimal and or maximal values consideration. That is the normalization. And during the normalization, what will happen? These weak peaks of absorption may be washed out. That's why we are not recording the absorbance, we are recording the percent transmittance. We are making the value larger. Simple is the thing. Absorption values are too small. We are making the values larger. You can see that we are keeping the transmittance between 15 to 70%. The path length is very small, 0.01 to 0.05 mm path length we are using. Here we are using the NaCl plates or alkali halide plates. Alkali halides are completely transparent to the IR region radiation. Quartz, glass, these are absorbing the IR region radiation. That's why we don't have to use quartz, we don't have to use glass, we have to use the alkali halide, that is the halogen salts in the IR spectroscopy. Whatever the prism or sample cell we are using, that is made up of these alkali halides. Okay, so you can make the distance between, you can set this path length by using the Teflon spacer or the gold spacer. It is possible to maintain such a fine, very small path length. Now we will see the instrumentation of IR spectrophotometer, that is dispersive IR spectrophotometer. In the earlier case, my friends, we have kept the monochromator before the sample, because the energy of UV light is very high and it can cause damage to the sample. It can damage or destroy your sample. That's why we are keeping this monochromator before the sample cell. But IR region radiation is having the low energy, it will not damage the sample. That's why in IR spectrophotometry we have kept the monochromator after the sample. You can see that a small difference is there between the instrumentation. We can use the various IR sources. You can use the incandescent lamp, Nernst glower lamp, glow bar lamp, mercury arc lamp. Various lamps are available which are producing the IR region radiation in various IR regions, that is near IR, far IR, mid IR. So various IR sources are available. Then reference and sample cell, I have told you it should be made up of halogen salts, alkali halides. Examples are NaCl, then another one is KBr, lithium fluoride. You can take many examples. Okay, so alkali halide is the material used for the prism as well as the reference cell. Then you can see that the best material is NaCl when you are doing measurement in the range of 2.5 to 10 micron. Here you can see that the grating monochromator is used in the earlier one. Instead of the grating monochromator, you can use the single pass prism monochromator. Here the slit is used, that we have to focus. In the another instruments of IR, the slit is not used, that we will see soon in the next slides. But here you have to keep in mind that in dispersive spectrophotometers, in dispersive IR spectrophotometers, we are using the slits. Okay, so IR radiation source is there, sample is there, slit is there. For reflection, litro mirror is there, plane mirror is there. In instrumentation you can see detector and recorder. A single pass monochromator is there. Best material for 2.5 to 10 micron is NaCl. Quartz is also used, but it is used only in near IR region, and alternative to it is lithium fluoride, that you have to keep in mind. But quartz is not completely transparent to whole IR region radiation. You can use it only in the near IR. Okay, so double pass monochromator, you can see that similar type of instrumentation is there. Grating monochromator, you can see that IR radiation source is there, then sample is there, slit is there. For reflection, the mirror is there, the reflected radiation is falling on the grating, then from the grating the diffraction is taking place, reflection is taking place, it is falling on the mirror, and finally the radiation is detected by the detector and the signal is recorded by the recorder. Okay, so here one more thing I would like to mention is that here 600 to 1000 grooves are there on the grating per centimeter. Now various sampling techniques we can use. We are familiar with the various states of matter, solid, liquid, gas. These are the basic three one. The advanced one are plasma, Bose, Einstein, condensate, and Higgs boson, God's particle. These are the 6 states of matter. Here we can analyze the 3 states. We can do the sampling of solids, we can do the sampling of liquids, we can do the sampling of gases. So first we will see the sampling of solids. So you can dissolve the sample in some non-aqueous solvent. Non-aqueous solvent I am saying because you are using the alkali halide plates, NaCl plate, and it will be damaged by the moisture. So we don't have to use the samples which are containing the moisture, or we have to use the non-aqueous solvent, so that our alkali halide sample cells should not be damaged, they should not become foggy, so avoid the water or moisture. So solid sample you can dissolve in a suitable solvent and you can record its IR spectrum. You can prepare a thin film of solid on the KBr or NaCl plate. You have to dissolve your sample in a suitable solvent. After dissolving in suitable volatile solvent, you can evaporate the solvent so that a thin film of your solid sample will form on the halogen salt plate, and you can record the IR spectrum. Then Mull technique is there. In Mull technique, you have to mix your sample with the Nujol, which is the heavy mineral oil. But the problem is that the Nujol is giving some extra peaks which are corresponding to Nujol. The peaks are given here. These four characteristic peaks of Nujol are incorporated into the IR spectrum, which may interfere with your interpretation of IR spectrum. Then pressed pellet method is there. In the pressed pellet method, we have to mix our sample thoroughly with the KBR, spectroscopic grade KBR. Very small sample we have to take, and very large quantity of KBR we have to take. We have to thoroughly mix it in mortar and pestle. Then we have to subject this mixture to very high pressure of 25,000 psi, pound per square inch, and then it is forming a pellet, a tablet. This tablet you can use for recording the IR. The advantage is that you can store this tablet properly, and you can reuse this tablet for recording the IR spectrum. But such a high pressure of 25,000 psi you are applying, so some polymorphic changes, some phase changes may occur due to the applied pressure in the sample. That is the disadvantage. Then sampling of liquids, you can take the mountable as well as demountable sample cells which are made up of NaCl, KBr, etc. Then it is possible to introduce your liquid sample between these halogen salt plates by using the hypodermic syringe. Very fine path length is there, 0.01 mm to 0.05 mm. So you have to use the hypodermic syringe to introduce your sample between the halogen salt plates. You can also do the sampling of gases, but in case of gases, the molecules are far apart from each other. They are loosely bound to each other, so we have to pass the IR radiation through this sample cell for a long time. So if you are increasing the sample cell length, the instrument length is increasing. Nowadays we are using the compact instruments. The length should not increase, but we have to pass the IR radiation through the same cell by multiple reflection, so that maximum radiation will be absorbed by the sample molecule. You can see that with the help of the reflecting surfaces, you can increase the path length. The same radiation you have to pass through the sample cell multiple times. Now we will see the FTIR interferometer. Earlier we have seen dispersive spectrophotometer. This is the FTIR interferometer. Okay, it is not using the slit. What is the advantage of not using the slit? That we will see. Okay, so here you can see that the coherent light source, that is IR radiation source, is there. Beam splitter is there. In the earlier case, it was the chopper which is passing the light in the pulsating manner, means it is passing the light in the discontinuous manner. Here, in a case of the FTIR interferometer, we have used beam splitter, which is splitting the beam, as the name indicated, splitter. One beam is reaching up to the stationary mirror, another beam is reaching up to the moving mirror. Now this mirror will reflect the beam, and the reflected beams will recombine at the beam splitter, and this recombined beam will reach up to the sample. The sample will absorb some of the radiation, and it will transmit rest of the radiation towards the detector. So when the signal detected by the detector will be maximum, and when it will be minimum. So it depends on this constructive interference and destructive interference. You can see that here we are moving the mirror, so it will be at different positions. So depending on the position of that mirror, reinforcement of the signal may take place, or cancellation of the signal may take place. Constructive interference may take place, or destructive interference may take place. Here we are recording the spectrum in time domain. We are not measuring every wavelength. In the time domain, just we are measuring the spectrum, and in one domain all the frequencies are considered. Okay, so here constructive interference is taking place when the optical path difference is 0, that is 0 optical path difference, or it may be lambda, it may be 2 lambda, means it is integral number multiple of wavelengths. Okay, so optical path difference, if it is 0, if it is integral number multiple of wavelengths, then constructive interference is taking place. If the optical path difference is half integral number multiple of the wavelength, then destructive interference is taking place. In this way, the signal may be between maximum to minimum depending on the interference taking place, constructive or destructive. You can see that the IR spectra is recorded in the time domain and it is converted into the spectra in, it can be converted into a spectra in wave number. Okay, so this calculation we don't have to do manually. We are having a Fourier transform FTIR instrument. So Fourier transform equation is given here in the slide. You can see that this automatically converts, this computer program automatically converts the spectrum from time domain into frequency domain. So we don't have to do the calculations manually. It is a very easy task. So what are the advantages of FTIR over the dispersion IR? First advantage is Felget advantage. You can see that it is possible to do measurement of all wavelengths simultaneously in time domain. With a single stroke, all frequencies for all the wavelengths will be recorded in the time domain. You don't have to do measurement at individual wavelength. But in dispersive spectrophotometer, every wavelength across the spectrum, whatever your spectrum range is there, along that range you have to record the absorbance or transmittance for every single wavelength. That is the disadvantage. It is time consuming. Okay. Now Jackinot advantage or higher throughput advantage is there. I have mentioned that, my friends, I have mentioned that we are not using slit here, so that the maximum radiant power should reach up to the detector. Maximum radiant power should reach up to the sample. When maximum radiant power is reaching up to the sample, it is doing absorption. Maximum radiation is absorbed. Maximum signal is reaching up to the detector. So signal to noise ratio is increased here. When signal to noise ratio is increased, it increases the sensitivity of the instrument, and it is possible to record very small peaks also. The sensitivity for the measurement of small peaks is increased. They will not be washed out. So this is the advantage. If you are not using the slit, then maximum radiant power is reaching up to the sample, signal to noise ratio is increasing, and even it is possible to record very small peaks. Further is cones advantage. So in dispersive IR spectrophotometer, we are using polystyrene as the external reference standard for calibration. But here in FTIR, helium neon laser is there, and this is working as an internal standard for the calibration of the instrument. So the precision of measurement is very high. We don't have to calibrate it by using the external standard. This is the difference between the two. The dispersive IR require an external standard, that is polystyrene, while FTIR do not require external standard. With the help of the internal standard, the calibration is taking place. So I hope you have enjoyed the lecture. You are enjoying the lecture. Attenuated total reflectance, that we will see. In the earlier cases, we have seen that we have to do sampling. You are mixing your sample with a Nujol, with KBR, Here in attenuated total reflectance we don't have to do sampling, or very little sampling is required. The instrument, you can see that it is ATR, it is having an alloy wheel, then it is having a crystal on which you have to put the sample. The crystal may be made up of various substances. Zinc selenite is there, you can see a list here. A zinc selenite crystal might be used, silver chloride crystal might be used, diamond can be used. These various material are having various refractive indices, and they are having various critical angle. It is summarized here in the table. So various materials we can use as an ATR crystal. So exactly below the tip of that alloy wheel, you can see that the ATR crystal is there, on which you have to put your sample. In ATR spectroscopy, the sample is in contact with the ATR crystal. The refractive indices of sample as well as the crystal are different. You are passing the IR region radiation. Total internal reflection is occurring there because of the difference in the refractive indices of sample as well as the ATR crystal. And during this phenomena, due to the difference in the refractive indices of both, evanescent wave is reaching up to the sample, and a part of evanescent wave will be absorbed by the sample. Based on the sample composition, a small part of the IR region radiation, a small part of the evanescent wave will interact with the sample, and it is resulting in a slightly attenuated, means reduced force. Its energy is reduced in slightly attenuated total reflection. The material we have already seen. Here is the mechanism. You can see that with the help of the triangle I have shown the ATR crystal. On the ATR crystal the sample is kept, infrared beam is passed, but very small part of this infrared beam, that is the evanescent wave, which is the quickly vanishing. Evanescent means quickly vanishing, means transient, which is persisting for very small time. That evanescent wave is reaching up to the sample, and a part of that evanescent wave will be absorbed by the sample. Okay, so this is the mechanism taking place here. Research relevance of IR. We know that IR is primarily used for functional group identification. There are many more recent advances in IR which can be used in research. You can see that the ATR can be used as a tool to probe the surface adsorption on nanoparticles at the liquid solid interface. Then you can study the clay mineral composition and its structure, and not only that, you can study the interaction of the clay minerals with various inorganic and organic compounds. Then you can study the various biological compounds at the cell membrane, present on the cell membrane, and you can determine what is their function. Then Fourier transform infrared spectroscopy can also be used for identifying the chemical bonds present in the particles which are isolated from the water. Many more applications are there. Due to the time bound, I have taken few of the representative examples. I have given the link here. Please do explore it. 2 links are given which are dealing with the recent advances, recent uses of IR spectroscopy in research. So thank you very much. We will meet again in the next session, in which we are going to discuss NMR spectroscopy. Okay, so thank you very much.